Hi everyone, and welcome to another physics lab. Today, we're focusing on two principal aspects of propagation of light. We will deal with polarization, which is another step in the domain of light after we've talked about reflection and refraction. So we're going to deal with polarization as well as forming an image using a lens that will fall under the topic of not refractive index, but the optic bench. So basically, this first part is the part that deals with the optic bench. I'm going to introduce you to the different apparatus you use for this particular experiment, and then I will conduct the experiment and let you see what actually happens. So what I'm trying to put here, this is kind of a bridge between what you did in the reflection and refraction, because we are still going to talk about the refractive index, right? When we talk about polarization, and we're going to bring a little bit of the lenses we did before. Remember when we did the lenses, it was like just, hey, lenses exist. Then we went to the mirror and the blocks, the glass block and the prism. But now we're going to bring the lens and really see how the lens manipulates light rays. We had the situation where the glass blocks was bending the light ray, and that was fine. We saw the image, but now we're going to look at how the lens, who's also a glass, manipulates the light rays and how that really affects the image. It's not just about ray tracing this time around. We're going beyond ray tracing. We're actually seeing when ray tracing is all said and done, what happens to the image or to the object or to the light ray. So those three things are involved. You have the object, the light ray, and the image generated by those. So here you have a light source, which is a desk lamp. You have a lens. You have two supports holding up a meter stick. Now that meter stick allows us to be able to get dimensions of length as with respect to the position of the object and the image. And you have this cardboard band. It plays the role of a screen. So essentially, we're going to have light coming out of here, and the object will be, let me go closer to the light bulb. The object will be the inscription you see on the light bulb. Those inscriptions normally prescribe the specs or the specification of a light bulb, but we're going to use them as our object. And the light ray coming out of that light source will go through the lens. It will travel, and it will be distorted because it's gone through a lens. It will be refracted, and it will end up on the screen here. So let's see what happens. So hold on a minute. I have to set this up for you guys to make sure you guys actually see what's going on. And then hold down the camera. So I'm turning on the light at the level of the light source. All right. And the whole idea here is to be able to slide the lens and see what happens to the image. So I'm sliding the lens, right? I'm going to take you guys closer to the screen so you see what will happen at the level of the screen. All right. Let's go to the screen as close as we can get. Again, we don't have zooming capabilities, so you guys are just going to bear with us trying to adapt here. All right, so I'll be sliding the lens and you observe what happens on your screen. There we go. There was a slight glitch there. Okay. Uh, so, for example, here is right here. What you're seeing is a tungsten wire in the light bulb. Okay, there's a tungsten wire in the light bulb. So the light rays cast the image of the tungsten wire onto the screen. But as I said, depending on where you put your origin, if we put our origin at the level of the image of the inscription on the light bulb, so my inscription on my light bulb is considered to be my object, and I slide my lens. As you can see, you can start reading. Can you see it clearly? I hope you can. I'm going to move you closer. So if you look at the screen, you can see the inscription that is normally on the light bulb appearing. I'm going to bring the camera closer so you can take a look. So hold on. I hope the visuals are good here. All right, so you can see something like an inverted 120 volts. This is an inscription that is normally on the surface of a light bulb, but the light rays has carried the inscription in the form of photons that are being casted onto the lens and projected the image of that inscription onto the screen. So we have successfully used the lens to project an image of the inscription of the light bulb onto the screen. Now, a couple of things we'll have to find out here. I want you to pay very serious attention to what you're seeing. The 120 is inverted. I hope you guys can see that. It's not 120 volt is written as if it was 150A, right? It's good to realize that the image is inverted. The image is enlarged because this is way bigger than the inscription on the light bulb. And finally, the image has been formed on the screen. Those are three properties you always have to verify. Is your image inverted or upright? Is your image enlarged or reduced? And is your image created on the screen or extrapolated in order to erase, or erase extrapolated in order to create your image? We will talk about that later on as we expand on this particular lab. But in the meantime, the other data you need to collect is the position of the lens. So if you look here, you see your light bulb is at, the light bulb is exactly 0 centimeters, right? I know you can't see the light bulb because of the glare, but you see the ruler or the meter stick starts where the light bulb begins. So the light bulb is at 0 centimeters. The lens, I'm going to have to turn around the lens. If you follow here, the lens is at 18 centimeters approximately. We cannot see all through, but we have 17, we have 19. We have 19. You can see that the lens is probably at 18 centimeter. And last but not the least, you have your screen, which is at 100 centimeters. So we have those dimensions, and we know the uncertainty of the meter stick is 1 millimeter, basically. That's uncertainty of a meter stick. So position of the object, which is the light bulb, is at 0 centimeter. Position of the lens, which is the lens, of course, is at 18 centimeters. And position of the screen, which is the cardboard paper, is at 100 centimeters. We're going to use that in our calculations in order to find what we call the focal length. I'll see you in the explanation regarding this lab.